All right, cool.
Holy.
What I do?
I like last week. I just like typed here and I didn't do it. You read it out loud.
Oh
Yeah.
It was so fast.
Okay. So last week we left off right here on 5.2. Please grab 5.2 out and let's get started on that. Does anyone still need a packet? What? I mean, kinda. You can hang on to it if you want to think about it. But.
Hey, Coach, can I have one?
Didn't I give you one? Yeah, that's what I said.
At least once in a month.
Excellent. Okay, so please listen. We left off here. Okay, we kind of had gone through a couple other new things as a part of 3 or 5.2. The main new thing that we went through was if I know the rate of any reactant or any product, and again, well, hold on, time out. What's rate for chemical reactions? What is rate? It is. What's Y and what's X? If I am measuring how fast the chemical reaction is going, what am I measuring it in terms of, or what's the units of that rate? Correct. Molarity per second, right? How does the molarity change over the course of time? So what we learned last week, Thursday, was if I know how fast one of these reactants is getting used up, or if I know how fast one of these products is getting made, I can also figure out how fast any of the other ones are being used up or created. We can use coefficients to compare rates. Okay, so this example was if I know that the concentration of X or the rate of X is 2.33, I can also figure out the rate of Y, right? How fast does the molarity change per second, per time? Okay, it doesn't have to be seconds, it could be minutes, but this was where we kind of left off, and then we got to 2 giant questions. Number 3 and number 4 on this sheet are kind of like a big summary of the first 2 topics, okay? We were right about here. I believe I had gone through C. Hopefully you have work all the way through that spot, I think. I'll recap, but it feels like it's been like a month again, but I know it was just a 4-day weekend for you guys, but it feels like a really long time. I don't know why. But the first thing we did here is we tried to determine the rate law. A rate law is an equation that allows us to find the rate at any given point in time. So rate equals K. K is what's called the rate constant. And then we multiply that rate constant by the concentration of the reactants raised to the order of their relationship with the rate. Now, in order to figure out the order, what we do is we analyze data. So I had 3 trials here, 2 different reactant molecules, nitrogen monoxide and oxygen gas. And if I look at trials where one of these is held constant, okay, for example, 1 to 2, their concentration of NO is held constant, the concentration of oxygen is tripled, okay, I can analyze how that change in molarity affects the rate of the reaction, right? So I saw that this rate or this concentration tripled, and as a result, I expect that the rate will change by the exact same factor raised to a power. The power that I raise it to is called the order. Okay, so this tripled, the rate also tripled. Great, it's a first order relationship. For the next chunk, we want to analyze the other reactant, right? I need to analyze these independently. So I want one to remain constant, the other one to change. From trial 1 and 3, you can see the molarity of oxygen is constant, but the molarity of nitrogen monoxide was triple. What happens to the rate? Well, it's going to change by the exact same factor raised to a power. The power is the order. So I see this triples, I automatically put times 3 over here, and then I just try to figure out the power of that. The hard part is when we're working with scientific notation, life gets a little sketchy. Okay, you might have to just plug these into the calculator and guess and check it out. Okay, I'm assuming you're not great at multiplying scientific notation by like 3 and 9 and 27 in your head. I'm assuming. Maybe you're pretty solid at it. I don't know. Don't want to throw judgment on you. Okay, but we figure out the power, that's the order. Now, from that, we can write out a rate law. Rate equals K times each of those reactants in brackets. Brackets means molarity. And then we just put them to the power that we figured out from the data. We figured out that nitrogen monoxide was second order. We figured out that oxygen gas was first order. And this is the overall equation that I get. Then, in part C, I asked you to solve for the value of the rate constant, K. So what did we do? We went back to our data table. We took the numbers from trial 1, and we plugged them into our equation. Okay, so I plugged in the rate from trial 1, 8.52 times 10 to the negative second, right there. I plugged in the molarity of the nitrogen monoxide for trial 1. I plugged in the molarity of oxygen gas for trial 1, and then I solved for K. Numerically, K ended up being 7.10 times 10 to the third, but you have to label the rate constant as well. When you label the rate constant, this is when you have to like think about what the heck's going on or think about the other units and labels in the problem, right? This is the way I've kind of been teaching it to you. If you take this exact same equation, okay, completely ignore the numbers and just write out the units and nothing else, the units or label on the left-hand side of the equation must match the units or label on the entire right-hand side of the equation, right? So we know that rate is molarity, or sorry, moles per liter times second. We know that this is molarity cubed, right? Because that's a molarity squared times another molarity is molarity cubed. And then I just fill in the blank. What does this need to equal? What does the unit or the label of K have to be so that this side of the equation matches this side of the equation? Okay, that was a crash course. How'd I do? Any of that ring a bell? That's rather inconclusive. You're going to get another shot at it here in 2 seconds. So, all right. So, if trial 1 was repeated, okay, if they did it all over again, they kept the molarities the same. They had 0.02 moles molarity of the nitrogen monoxide, 0.03 molar for the oxygen. If they kept the molarities the same, but instead they had these two gases react with one another in a bigger reaction vessel, okay, in a bigger container, whatever you want to call it. Would we expect this to go faster or slower if I have these two gases in a larger container? Don't yell at me just yet. Think about it, okay? I have a chemical reaction. I've run it once. Here's the data from trial 1. The rate is this fast. I run this exact same reaction one more time, but I've increased the volume, meaning it's a bigger reaction chamber. Is this going to go faster or slower if I have these two gases in that new vessel? Talk to your neighbor. What do we think? Thumbs up for faster, thumbs down for slower. That's like a cop-out. You got to commit. Double commitment. Nice. Yes, it should go slower. Now, the question is why? Okay, why? Your intuition is correct, but why? Why, if I have this happening in a bigger chamber, would it not go as fast? Jack?
Well, it would, if it's a bigger chamber, it'd be like more liters of the gas and the concentration would be smaller, or less.
Sure, I'll accept that. That's one way of thinking about it. The molarity is actually less if the volume is bigger. Yeah. There's another thing that I would accept too. Another answer that's pretty good. What needs to happen in order for a chemical reaction to occur? They need to collide. And if there's more space, correct, the likelihood of collision is less. There's going to be less collisions with a bigger volume or more space, which would also slow it down. So I would accept either of those answers. Those are both great. Okay, so slower, I would say less collisions. Or again, you can totally say lower molarity. That's effectively saying the same thing. Because the reason why molarity changes the rate is because lower molarities, there's less particles, so less collisions, right? It all kind of comes full circle. Kind of the same argument, just a different way of saying it. All right, I'm going to shut up for a little bit. And I want to see what you can do. You can work with one another. That's fine. You have your old note sheets. What?
I need it right here. I want to sit like right there.
Okay, I can help you. I can help you. Use 5.1 if you need to. The previous problem is more or less the same, so there's that as well.
Yeah. Hello? Yeah. Stays the same. I want one. Try one and two.
Like between these two columns or between.
I didn't see the zeros. Each trial is only independent. So what I want is switch the arrows. If I want to analyze, how this reacts from how this reacts. Wait.
But they all change.
No, it's incorrect. So that's how I would do it. Now let's look at 1 and 2. Yeah. Try one and try. Yeah. This one. So then what's like great? See, I didn't pay. I assume that's also. Try one.
Try 1, 2, it's not, they're not, like, if you want 2 or 1, it's double, because that's like, there's another. Yeah, if you like, I mess up at first too.
Let's act like. Yeah. They're both different. Increases the really off of what we do. The problem is, yes. So see, if you like, yeah, I can only add. So. Well, that's all. So what I do is I want to play one of them. Now, this is pretty. So from trial 2 to trial 1, what happens when let's be more specific. We want Yeah, but that's annoying. So let's only do so instead of saying for trial 1, we go trial 2. Let's go from trial 2 to trial 1.
1 minus.
Now, however we square that, the rate will change by the exact.
This one.
Yeah, we're doing for the.
So automatically, without even thinking about it, we have an arrow from there to there.
Oh, sure. Now we have to do.
So that's times 2. And now we're this is times 2.
But you know, it's times 8.
Yeah, you know what's going on to the.
Now, we want to do the exact opposite. We want to throw one here. This one, check. This is probably.
Yeah, that's cool.
I didn't keep it.
Yeah, you know you're doing.
Don't you see?
Wait, it's just.
A nice piece. We give you different data. Or data. But we can still talk about this idea. Hey, this is the same. I know all this is so, let's go. Maybe let's go right here. From trial 3 to trial 2. Okay. From trial 3 to trial 2, this doubles. We know that as we double that, this should go back after 2.
Well, yeah, because this one.
I don't know. So
That's the easiest.
Oh, I see what you're saying.
So now let's change it. So this bubble, we know this goes up by a factor like this. This is about got to be more than this. You gotta figure it out. I'll go all. If this was where, yeah.
Yeah, this was taking like a second. So then we want yes, and this one is times 8 by itself.
Wait, you have to this one.
You're comparing.
Well, I don't know how that goes up. That times 2, that times 4. I know.
What's going on?
How's the struggle? No, it's not a trick question. It's a poor set of data.
Yeah, that's.
Because whoever set it up, this guy, didn't give you nice trials.
Okay.
No, it's perfectly reasonable, but it's not a way that a real scientist would set up an experiment. Because a real scientist would just isolate their variables and, run 3 trials and you're good to go. But I'm purposely making it annoying. Okay, so hang with me. Let me give you this whole overview one more time, okay? I have a reaction and I want to monitor the rate, right? Some scientist has run 4 trials on these 2 reactants, changing the concentrations throughout the trials. And the goal here is to figure out the rate law, figure out the equation that allows us to compare molarity with rate. okay? And we need to figure out the order of what we got going on. So in an ideal world, we find trials where one of these is constant and the other one changes. That's ideal, because then I know whatever one is changing is the one that messes with my rate, okay? If this is the exact same molarity, this can have no effect on that changing, right? That makes sense? It didn't change. So if this didn't change, that couldn't possibly have affected how fast it's going. So whatever change occurred must have been because of this, right? It must have been because of the reactant that actually did change. So let's look at trials 2 and 1. From trial 2 to trial 1, what happened to this molarity? It doubled. Now, you can go the other way, right? But that's a little more annoying. I like to always go in the positive direction. I like making the molarity increase because it's much more friendly than like having this be like divided by 2 or have this be like multiplied by 0.5. Eh. Does it work? Sure, it works, but it's a little more annoying. Okay, so I tend to go from lower molarity to higher molarity, and that's perfectly okay. These trials are independent. Okay, I said that last week too. These trials are perfectly independent, meaning because I call this one number 1, that doesn't matter. I could call this one number 1 or that one number 4 or that one number 2. It doesn't matter. They're independent. So the order is irrelevant. I can compare any one trial to any other trial. Okay, so this doubled. However, the molarity changes. The rate changes by the exact same factor, raised to a power. So without even thinking, I do this. Now I start to think, okay, did this double? Did this triple? Did it, quadruple? What did it do? Okay, it's going to be something times 2 raised to a power. Is it 2 to the first, 2 to the second, 2 to the third? What is it? Okay, well, what is it? 2 to the first, right? This is easy scientific notation math. I think you can see that and look at it and catch it, right? Okay, right on. Right, yep. For the next one, we want to figure out this other reactant, right? We figured out the order of the iodide. The iodide is a first order reactant. So if I double the iodide, the rate's going to double. If I quadruple the iodide, the rate's going to quadruple. We know the relationship now for this one. So any change over here, we know it's that exact same change raised to the first power over there. We know that. Now, in an ideal world, like I was saying, the chemist would have set this up so that this molarity was constant between 2 of the trials. They didn't do that. And by they, I mean this guy. Okay. Should they have? Yes. That makes life way easier. But we don't necessarily need it because we're smart and we can figure this out. So I'm going to pick 2 trials that are just kind of sort of friendly, I guess. I'm going to pick 3 and 2. Do you have to pick 3 and 2? You don't. Okay, there's other ways to do this, but I'm going to pick 3 and 2 because I want to. I know that doubles. I know this doubles, right? You see that? Now here's the deal. This is doubling. That is doubling. I know for a fact that this must be going up by that exact same factor. Now the question is, what's the power? What's the order? I know some of it. I know that this change will force the rate to go up by a factor of 2 to the first. We already figured that out, right? Any remainder or any additional change must have happened because of this reactant. See what I'm saying? I know how this is going to mess with the rate. I don't know how this is going to mess with it. So if I can understand this double, okay, this must, at a minimum, it must, at a minimum, double. Any additional happened because of that. Following my logic? So how much did it change by? What's the order here? 2 to the what? And if you need a calculator, that's okay, because it is scientific notation. Yeah, what's the total change? Should be 2 squared. If you don't believe me, please take 9.88 times 10 to the negative third and multiply it by 4 in your calculator. Yeah, now we got to think a little bit, right? So the total change is 2 to the 2 squared. Half of that change was because of this. We know that this, when the iodide doubles, the rate doubles. So we have 2 to the first as a result of this, which means the other 2 to the first must be a result of the other one. So in other words, this is first order. We figured that out from trial 1 to 2. And the other one, the OCL, that I have, is also first order. Okay. Now, this is hard because I gave you bad data. Life is much easier when I do this. Okay, if you look back at this one, which we did last week, Thursday, this this triples, that's constant. Nice. This triples, that's constant. Nice. We're analyzing one variable at a time, right? This doubles at the same time. So we have to account for both of those changes. We figured out what this one is first, so we knew what it was going to do. Any remaining change, or remaining, that's not a word. Remaining, let's drop the D there. Why I teach science. Any remaining change is because of the other. They are both first order. Okay. Continue forward. I don't think you need me for the rest of this, I hope. We'll see. What I'd like you to do is figure out the rate constant K. You now have the equation that you need. Plug numbers in. Take the equation that we just solved for and plug values in from trial 1 to solve for K. When you do so, also label it appropriately. And if you're all done, because this kind of makes sense, I don't know how many people that applies to, but if you are all done with this, you're welcome to jump into the homework and take a peek over there. Well, there's always homework. It's just not for a little bit. I got more to teach you. The first assignment's actually a front and a back side.
First order means that however you choose the rate change by first power.
Yeah, okay, that makes a lot of sense. I think I knew that, but sure, the reason why I think of the Star Wars.
I'm sorry. Yeah.
I was just.
This is not Star Wars class. This is chemical kinetics.
I was just.
So do you think?
So awesome.
I-
Okay, this makes my brother asked that. We are. She was like, I'm making this.
We want in the real world.
I mean,
We don't get your own finish. Mostly cardio.
Yeah. What did you get?
Yeah, that is so good. I feel so cool when I do
It
it.
is really fun. So you have the mod. You have the mod.
Hey. Oh, no, we had the Oculus Quest too, so installed right on.
Oh, I
Make sure I get-
Yeah, so.
I mean, that's good.
You can't pirate anything, it's all.
Yeah, so I know
Yeah. Yeah. Yeah, you gotta like buy, it's not crazy, you can buy like a whole house.
Yeah.
A whole for this people for like $5. This one's it's really fun. The hardest level. I didn't expect those. You know how many those people sell them. This one doesn't have any more power. This one- it doesn't have the amount of blocks. And then on expert and expert plus expert, they like double the blocks and triple the speed. You have to so fast. I made about 3 I tried to, I didn't increase it on my own. Because you have to really, you're spinning in the so fast. I It is fun.
All right. I'm going to plug numbers in from the first trial. Come on, work. There we go. I have a rate of 7.91 times 10 to the negative 2. I have a K value, which I don't know. That's what I'm trying to solve for. I have a molarity of iodide equal to 0.12. And I have a molarity of OCl, which is hypochlorite, equal to 0.18. Now it's just algebra and solving for K. What do you get for a value of K?
3.66. You need the like times like say what scientific notation
Yeah,
times 10 to the 0. Is that a thing?
it's a thing. That means it's just that.
Then yeah, so that's what I thought. I was like, can I just do that?
Sorry, you guess.
Okay, I didn't know if you still had to write it out.
No, only if it's not due to the 0. Right? So it's this?
Yeah.
Cool. What's the label? Correct. Now, there's two ways to think about this. You can either work this out and solve for it by doing the same equation with no numbers and just labels, right? So I could set that up as mole divided by liter times second. That's rate. I know rate is always that label. K, I don't know. This is molarity. That's molarity. So that's just molarity squared. And now I fill in the blank, right? So what am I missing? Well, I have one too many moles on top, so I need to cancel one of those. I have one too many liters on bottom. I need to cancel one of those, and I'm missing the seconds chunk. And there's my label of K. Or, if you know the overall order, meaning, okay, this is first, that's first, overall, it's second, right? We just add those up. My label is liters to the order minus 1 divided by moles to the order minus 1 times seconds. So liters to the order, which is 2, minus 1 is 1, liters to the first, divided by moles to the order minus 1, 2 minus 1 is 1 times second. So if this was fifth order, right? If it was a fifth order reaction, I would have liters to the fourth, moles to the fourth times second. If it was eighth order, I would have liters to the seventh, moles to the seventh times second. One less than the order, liters over moles. Cool? Jigger?
So the seconds is always attached to moles.
Correct, unless it's minutes. I haven't done that to you yet, but it could be minutes. The unit of time would be in the denominator. It's not always seconds, it's almost always seconds, but sometimes it is minutes.
Okay, so what's the deal with minutes?
Nothing, just a different unit of time. Calculate the initial rate of a fifth trial, where I and OCl are both 0.15. We're using the same equation. Rate is what I want to solve for, I don't know what it is, equals K. I know what K is now, don't I? Now it's the same because we know what it is. We just solved it.
Okay, and then
Not going to change. Nope.
okay. Even if you like add stuff.
Depends upon what kind of stuff you're adding, but
What would adding like energy do?
like changing the temperature.
I don't know, something.
Yeah, changing the temperature would change the value of K,
Okay.
but we're not doing that. Yes,
So
Jake.
is adding electricity count as adding temperature?
Electricity and temperature are different,
I
but generally a flow of electrons does change the temperature because some of that energy is dissipated as heat. It's getting kind of physics. Though. There's your setup, right? I didn't use any labels, but we know what the rate value or the rate units are at the end anyway, right? What do we get for a rate? Good. What'd you get?
When you write it in scientific notation and when do you not?
Doesn't matter. As long as it's right, it's right. Totally up to you. So if you wrote this as 0.00824, cool. Yep.
It's like,
Questions? What was that? The label is the rate, right? Always make sure you know what you're solving for. Rate constant, which is K, this thing, has a different label every time, basically. It depends upon what the overall order is. But when we're solving for rate, rate is the label that it's always going to be, moles per liter times seconds, most likely. Okay. Last one. If the experimenter wanted to speed up the rate of this reaction, list 3 things they could do to achieve this. What 3 things could the experimenter do to make this go faster? Okay. Think about that. And if you're not quite sure, there's a bulleted list of things that change the rate of reaction on the front side of 5.2.
What's an add catalyst? I don't know what they are.
It is.
Would that add it?
Oh, wait, okay.
Add catalyst.
So like,
Add catalyst. Make it
more
smaller.
concentrated.
Wait, is this gas?
Concentrated.
I don't know. Is it?
No, it's,
Are these gases?
I doubt it.
But then there's also more chance of.
Oh, so then. with the volume-
That is on your sheet, right? Yeah. Okay.
With the volume. change-
Wait, do we have to say specifically?
I don't know.
what?
No, I don't think so.
Mr. Baraza,
Yes.
would we have to say like a higher?
Just something needs to-
concentration or lower reaction concentration?
What?
You have
What's the difference?
I think more should say less and honestly not less.
Remember when they I'm saying all 3 steps.
Yes.
So if I have more stuff, I have more fluid. In total, right, so the rate is like how much is changing. It's not like how long does it take. Yeah,
We're not solving for.
yeah. How much reaction-
Yeah.
Hang it.
This is the problem. You get the wrong person.
All right. What can we do? Decrease the volume of the container. Let's talk about that.
Actually, you're right, if it's not a gas.
Now, okay, so if it's not a gas, right, that doesn't really work because, again, this is all aqueous. So let me phrase it a different way, okay? If I kept the moles of stuff the same, but got rid of volume of liquid, meaning I'm increasing their molarity, that works. Now, that use of the word volume is different in those two scenarios, right? I'm talking about like liquid volume for an aqueous solution versus like volume of a container for a gaseous reaction. But if you change the concentration, okay, if I increase the concentration of either of the reactants, okay, it will go faster. If I increase the molarity of either of the reactants, it's going to go faster. What else? Add a catalyst. What's it going to be? I don't know. But in theory, if there were a catalyst that was applicable to this reaction, it would speed it up. Yeah, so we're just generically going to say add a catalyst. Okay. Now, trying to determine what that would be in a different scenario completely depends upon what kind of chemistry we got going on. Okay? And offhand, I don't know what that would be in this instance. But generically, yes, add a catalyst. What else? Yeah, crank up the temp. Okay? If you increase the temp, it's going to go faster. Why? More collisions. Yeah. Anything else? What else is on the front? I think that was it, wasn't it? Yeah, how can we change the surface area? What?
You reduce the surface area, is that like speed up the rate
Of what? Here's the problem.
Oh, yeah, it's in.
Surface area is about solids, yeah. If it's not in a solid phase, how can you increase or decrease the surface area of an aqueous substance? The chemical is what it is, right? I have iodide, and I have hypochlorite, OCl1-. I can't increase or decrease the surface area of either of those if they're just floating around in liquid, right? They're aqueous. So surface area doesn't work unless you're talking about solids. The example I gave you on the front was aluminum powder versus like aluminum foil, like crumpled up into a ball. Yeah, that would make sense, right? Then that totally works. All right, cool. What you got?
Is there anything else you could do with it?
Maybe. Depends upon the reaction.
Well, with this reaction, is there anything else you could
Those are the big ones. We'll leave it like that. Yes, Chase.
So are there reactions that go faster, like are better when they're like in colder temperature?
No, the rate. Hold on. There's two things at play here. Okay, because you're probably thinking of like something that's like endothermic.
Yeah.
Or like I'll talk about that later, but the rate will always increase with more temp and decrease with less temp. Always. However, once we get to equilibrium, okay, we have two competing reactions sometimes, one going forward, one going backwards. And then sometimes an increase or a decrease in temperature will favor one of those over the other. So generally speaking, though, if I increase the temp, both ways are going to go faster. It's just the ratio might be different. And if I cool the temperature, both rates are going to go slower. It just might mess with the ratio. But yes, I will revisit that completely once we get to Unit 7, because that is a huge misconception. All right, I have 8 minutes. I'm not going to jump into 5.3. I'd rather have you take a peek at your first homework assignment. Once you get to the bottom of the first page, it's new stuff, and I haven't taught you yet. But the top half of the first page, or pretty much the whole first page, is all of this stuff. So 5.1, homework 5.1, that's going to be due next week, Tuesday. A week from today, quite a ways out, but how about next week, Tuesday? People at home, you're free to go. Have a lovely day. We'll catch you tomorrow.
I forgot to say.